the clock strikes 12. Somewhere in the stillness of a room, the hands of a timepiece align at the apex of their circular journey, and in that singular moment, one year dissolves into another. The midnight chime fades into silence, its resonance absorbed by the walls, the curtains, the quiet furniture that bears witness to this invisible threshold. Happy New Year. Outside, the last echoes of fireworks drift through the cold air, their brilliant colors already becoming memory. Their thunderous celebration settling into the hush that follows all great pronouncements. A calendar page, worn at the edges from 12 months of turning, hangs in anticipation of being replaced. 365 days have passed since the last time this ritual unfolded, yet the passage feels both impossibly long and startlingly brief. The human mind, in its peculiar relationship with duration, holds contradictions like this with ease. A year can stretch like an ocean when lived through, yet compress into a single breath when remembered. In quiet rooms around the world, clocks continue their patient work. The second hand sweeps its eternal circle, each tick a tiny heartbeat in the vast body of time. These mechanical witnesses mark the transition without judgment, without ceremony beyond their reliable rhythm. They do not know that humans have decided this particular rotation of the earth holds special significance. They simply continue, as they always have, measuring what flows through them. The concept of the new year is itself a human invention, a stake driven into the continuous river of moments to create the illusion of beginning and ending. The earth does not pause in its orbit around the sun. The stars do not acknowledge the change in human calendars. Yet there is something profoundly necessary about these demarcations, these agreed-upon moments when humanity collectively pauses to acknowledge the passage of time. The Gregorian calendar, the system by which much of the world measures its years, was introduced in 1582 by Pope Gregory XIII. It refined the earlier Julian calendar, which had been drifting slowly out of alignment with the astronomical seasons. The Julian calendar, implemented by Julius Caesar in 45 BCE, assumed a year of exactly 365.25 days. But the actual tropical year, the time it takes for the Earth to complete one orbit relative to the vernal equinox, is approximately 365.2422 days. This seemingly tiny difference of about 11 minutes per year had accumulated over centuries into a drift of 10 days by the 16th century. Such is the nature of time and its measurement. Small discrepancies invisible in the span of a single lifetime grow into significant errors across generations. The keepers of calendars must always reconcile human systems with celestial mechanics, and the reconciliation is never perfect. Even the Gregorian calendar, more accurate than its predecessor, will drift by one day every 3,236 years. In the deep future, adjustments will again be necessary. The weight of looking backward presses gently against consciousness in these midnight hours. Memory, that strange companion to time, offers up fragments of the year just past. Faces, places, moments of laughter and sorrow, decisions made and paths not taken. Memory does not preserve time faithfully. It edits, condenses, emphasizes, and forgets, according to patterns that remain only partially understood by science. Research in neuroscience suggests that memories are not stored like files in a cabinet, waiting to be retrieved unchanged. Instead, each act of remembering is an act of reconstruction. The brain reassembles memories from distributed neural patterns and, in doing so, subtly alters them. This means that the past, as it exists in human consciousness, is never quite the same as the past as it actually occurred. Time once lived becomes a kind of fiction we tell ourselves about who we have been. The philosopher Augustine of Hippo, writing in the 4th century, contemplated this mystery with remarkable depth. He observed, "What then is time? If no one asks me, I know what it is. If I wish to explain it to him who asks, I do not know." This ancient puzzlement remains strikingly relevant. Time is the most familiar aspect of existence, the medium in which all experience unfolds, yet it resists easy definition with stubborn persistence. Augustine understood that time seems to exist in 3 modes: the past, which is no longer, the future, which is not yet, and the present, which has no duration and constantly slips away. Where then does time actually reside? His answer pointed toward consciousness itself. The past exists as memory, the future as expectation, and the present as attention. Time, in this view, is inseparable from the mind that perceives it. The forward gaze of anticipation accompanies the backward gaze of memory in these threshold moments. The year ahead stretches like an unwritten page, full of potential and uncertainty. The human relationship with the future is characterized by a mixture of hope and anxiety, planning and surrender. Unlike memory, which deals with events that have already crystallized into fact, anticipation engages with probability and possibility. Psychological research reveals that humans are remarkably poor at predicting their future emotional states. This phenomenon, called affective forecasting error, shows that people consistently overestimate both the intensity and duration of their emotional reactions to future events. The promotion imagined to bring lasting happiness, the setback feared to bring lasting despair. Both tend to affect well-being less dramatically and for shorter periods than predicted. Time, it seems, has a way of absorbing shocks and returning consciousness to its baseline. Beyond the personal and psychological dimensions of time lies the physical reality that science has slowly unveiled over centuries. The nature of time in the physical universe is stranger and more wonderful than everyday intuition suggests. The clocks that tick in human homes, the watches that encircle human wrists, the digital displays that flash in human pockets, all participate in a phenomenon far more complex than their simple faces reveal. For most of human history, time was assumed to be absolute. It was thought to flow uniformly throughout the universe, the same for all observers, unaffected by motion or gravity. This intuition, formalized by Isaac Newton in the 17th century, served humanity well for centuries. Newtonian mechanics, built upon the foundation of absolute time, enabled the prediction of planetary orbits, the construction of bridges, and the engineering of machines. Newton wrote of absolute time as that which, from its own nature, flows equably without regard to anything external. This conception imagined time as a great cosmic clock, ticking away identically everywhere, providing a universal reference against which all events could be measured. It was a comforting picture, suggesting an ordered universe with a single shared timeline. The revolution came in 1905, when a young patent clerk in Bern, Switzerland, published a paper that would transform physics forever. Albert Einstein, at the age of 26, proposed his special theory of relativity, and in doing so shattered the notion of absolute time. His insight began with a deceptively simple premise. The speed of light in a vacuum is constant for all observers, regardless of their relative motion. This single postulate, combined with the principle that the laws of physics are the same for all observers in uniform motion, led to astonishing conclusions. Time, Einstein showed, is not absolute but relative. It flows differently for observers, moving at different speeds. A clock in motion runs slower than a clock at rest, a phenomenon known as time dilation. This is not an illusion or a mechanical effect. It is a fundamental property of space-time itself. The equations of special relativity reveal that as an object approaches the speed of light, time aboard that object slows dramatically relative to a stationary observer. At exactly the speed of light, time would stop altogether. This is one reason why massive objects cannot reach light speed. It would require infinite energy to accelerate them to a velocity where time ceases to flow. Einstein himself reflected on the strangeness of his discovery. He wrote, "The distinction between the past, present, and future is only a stubbornly persistent illusion." This statement suggests that from the perspective of physics, all moments in time may exist with equal reality. The present moment, which feels so uniquely immediate and real, may not hold any special status in the fundamental structure of the universe. 10 years after special relativity, Einstein completed his general theory of relativity, extending his insights to include gravity. In this framework, gravity is not a force in the traditional sense, but rather a curvature of space-time caused by mass and energy. Massive objects bend the fabric of space-time around them, and this curvature affects the flow of time. Near a massive object, time runs slower than far from it. This gravitational time dilation is not merely theoretical. It has been confirmed by numerous experiments and has practical consequences for modern technology. The global positioning system, which relies on precise timing signals from satellites orbiting Earth, must account for both special and general relativistic effects. The satellites move at high speeds, which causes their clocks to run slightly slower due to special relativistic time dilation. But they are also farther from Earth's gravitational field, which causes their clocks to run slightly faster due to general relativistic effects. The net result is that GPS satellite clocks run faster than ground-based clocks by approximately 38 microseconds per day. Without relativistic corrections, GPS positioning would accumulate errors of roughly 10 kilometers per day, rendering the system useless for navigation. Every smartphone finding its location, every aircraft navigating by satellite, every ship crossing an ocean relies on Einstein's century-old insights into the nature of time. The precision of modern timekeeping has reached extraordinary levels. Atomic clocks, which measure time by counting the oscillations of atoms, can maintain accuracy to within a second over tens of millions of years. The cesium-133 atom, which oscillates 9,192,631,770 times per second when exposed to microwave radiation of the correct frequency, has served as the definition of the second since 1967. More recent developments in optical atomic clocks have pushed precision even further. These devices use atoms that oscillate at optical frequencies, hundreds of thousands of times faster than cesium. The best optical clocks would neither gain nor lose a second over the entire age of the universe. Such timekeeping precision is not merely an academic achievement. It enables tests of fundamental physics and may one day redefine the second itself. The physicist Richard Feynman, known for his ability to find wonder in physical phenomena, once remarked, "Time is what happens when nothing else does." This playful observation points to a deep truth. In an empty universe with nothing happening, would time have any meaning? The flow of time seems inseparable from change, from events occurring, from the universe doing something rather than nothing. The connection between time and change leads to one of the most profound questions in physics. Why does time seem to flow in only one direction? The fundamental equations of physics, for the most part, make no distinction between past and future. They work equally well whether time runs forward or backward. Yet human experience is asymmetric in time. Eggs break but do not unbreak. Ice melts but does not spontaneously freeze in warm rooms. Memories are of the past, never of the future. This asymmetry is connected to the concept of entropy, a measure of disorder or randomness in a system. The second law of thermodynamics states that the total entropy of an isolated system tends to increase over time. Disorder grows. Organized structures decay. Energy spreads out from concentrated regions to become more evenly distributed. The arrow of time, as this directionality is called, appears to be a consequence of the statistical behavior of large numbers of particles. There are vastly more ways for a system to be disordered than ordered, so random processes tend to move systems toward disorder. A shattered egg represents a much more probable arrangement of matter than an intact egg, which is why eggs break and do not unbreak. The British astrophysicist Arthur Eddington, who led the 1919 expedition that provided early confirmation of general relativity, coined the phrase arrow of time and emphasized its significance. He wrote, "The law that entropy always increases holds, I think, the supreme position among the laws of nature." For Eddington, the second law of thermodynamics was not merely one physical principle among many, but the fundamental fact that gives time its direction and makes the universe historical. Yet the origin of the arrow of time remains somewhat mysterious. Why did the universe begin in a state of low entropy, from which entropy could increase? This question points backward to the Big Bang, the origin of the observable universe approximately 13.8 billion years ago. In its earliest moments, the universe was in an extraordinarily ordered state, a smooth, hot, dense plasma from which all current complexity has emerged. The Big Bang was not an explosion in space, but an expansion of space itself. In the first fraction of a second, the universe underwent a period of exponential expansion called inflation, growing from subatomic to cosmic scales in an instant too brief to comprehend. Time as humans understand it may have begun with this event, though what came before, if before, even has meaning, remains unknown. The cosmic microwave background radiation discovered in 1965 provides a snapshot of the universe as it appeared about 380,000 years after the Big Bang. This faint glow, detectable in every direction of the sky, represents the oldest light in the universe. It has been traveling through space for 13.8 billion years before reaching modern detectors. Looking at this radiation is looking back in time to an epoch when the universe was 1,000 times smaller and 3,000 degrees hot. Light travel time is one of the most remarkable aspects of observational astronomy. Because light travels at a finite speed, approximately 299,792 kilometers per second, looking at distant objects means looking into the past. The sun appears as it was about 8 minutes ago. The nearest star system, Alpha Centauri, appears as it was 4.37 years ago. The Andromeda Galaxy, visible on clear nights as a faint smudge of light, appears as it was 2.5 million years ago. This means that the night sky is a mosaic of different times. Stars at various distances present light from various epochs, creating a temporal panorama. Some of the stars visible to the naked eye may have already died, their light still en route. Others may have been born since their light began its journey, but remain invisible because their first photons have not yet arrived. The astronomer Carl Sagan captured this wonder eloquently. He observed, "The cosmos is all that is or ever was or ever will be. In this vast temporal expanse, human existence occupies an almost imperceptibly small fraction. If the history of the universe were compressed into a single year, with the Big Bang occurring at midnight on January 1st, all of recorded human history would fit into the last few seconds before midnight on December 31st. This perspective of deep time can induce a kind of temporal vertigo. The age of the Earth alone, approximately 4.5 billion years, exceeds easy comprehension. For the first billion years, the planet was too hot and violent for life. The earliest evidence of life dates to about 3.5 billion years ago, simple single-celled organisms that left their traces in ancient rocks. For billions of years, life remained microscopic, its evolution imperceptibly slow. Complex multicellular life emerged only in the last 600 million years. The dinosaurs dominated for roughly 165 million years before their extinction 66 million years ago. Anatomically, modern humans have existed for perhaps 300,000 years. Agriculture began about 10,000 years ago. Writing was invented about 5,000 years ago. The scientific revolution is only a few centuries old. Each of these timescales reveals different rhythms of change. Geological time operates on cycles of millions of years, with continents drifting, mountains rising and eroding, ocean basins opening and closing. Biological time operates on cycles of thousands to millions of years, with species emerging, adapting, and going extinct. Human cultural time operates on cycles of years to centuries, with civilizations rising and falling, technologies transforming societies. The geologist James Hutton, often called the father of modern geology, recognized the vastness of Earth's history in the late 18th century. Examining rock formations in Scotland, he concluded that the Earth was immensely old, far older than the few thousand years suggested by literal readings of religious texts. He wrote that he saw no vestige of a beginning, no prospect of an end. This recognition of deep time was one of the great intellectual achievements of the Enlightenment. Within the human body, time operates on its own scales and rhythms. The biological clock, governed by a cluster of neurons in the hypothalamus called the suprachiasmatic nucleus, synchronizes bodily functions to a roughly 24-hour cycle. This circadian rhythm, from the Latin words meaning about a day, influences sleep, hormone release, body temperature, and countless other physiological processes. The circadian clock evolved over billions of years in response to the daily light-dark cycle caused by Earth's rotation. Even organisms without eyes, including some bacteria and plants, possess circadian rhythms. In humans, the circadian clock is reset each day by exposure to light, particularly the blue wavelengths present in sunlight. This is why exposure to bright screens before sleep can disrupt the body's natural timing. Beyond the daily rhythm, human biology operates on longer cycles as well. Women experience roughly monthly cycles governed by hormonal fluctuations. Seasonal affective changes alter mood and energy in response to changing day length. The aging process itself represents a kind of biological time, with cells accumulating damage, telomeres shortening, and systems gradually declining over decades. The science of chronobiology studies these temporal patterns in living organisms. Research has revealed that nearly every cell in the human body contains its own molecular clock, with genes that turn on and off in regular cycles. These peripheral clocks are coordinated by the master clock in the brain, but can also be influenced by factors such as meal timing and physical activity. The experience of time passing varies dramatically depending on circumstances and state of mind. A watched pot, as the saying goes, never boils. Time seems to drag when attention is focused on its passage, when nothing engaging occupies the mind, when circumstances are unpleasant. Conversely, time seems to fly when attention is absorbed in activity, when experience is rich and varied, when circumstances bring pleasure. Psychological research has explored these subjective variations in time perception. One factor is the amount of new information being processed. Novel experiences, which require more mental processing, tend to expand subjective time. This may explain why childhood summers seem to stretch endlessly, while adult years flash by. For a child, everything is new, requiring attention and encoding. For an adult, much is familiar, passing without leaving distinct memory traces. The philosopher Henri Bergson distinguished between the time measured by clocks, which he called spatialized time, and the time experienced by consciousness, which he called duration. For Bergson, duration was the more fundamental reality. The clocks and calendars that divide time into identical, interchangeable units miss something essential about how time actually feels from within. Bergson wrote, "Time is invention, or it is nothing at all." By this he meant that genuine duration involves the creation of novelty, the emergence of the new. Each moment is not merely a repetition of what came before, but a genuine addition to reality. The future is not already determined, waiting to be discovered, but is genuinely created as time unfolds. The relationship between time and consciousness presents some of the deepest puzzles in philosophy and science. Why does consciousness seem to ride the crest of an ever-advancing present moment? Why do humans experience time as flowing rather than simply existing all at once? These questions touch on the hard problem of consciousness itself, the mystery of how physical processes in the brain give rise to subjective experience. Some philosophers have proposed that the flow of time is itself an illusion, that all moments exist equally in a four-dimensional block universe. In this view, influenced by the mathematics of relativity, past, present, and future are all real, and the sense of moving through time is a psychological phenomenon without fundamental physical basis. Others argue that the passage of time is genuinely real, that the present moment has a special status not captured by the block universe picture. The physicist and author Carlo Rovelli, known for his work on quantum gravity, has written extensively about the nature of time. He suggests time is ignorance. What he means is that the apparent flow of time may be related to the limited information available to observers within the universe. If one knew the exact state of every particle, past and future might appear equally fixed. But because such knowledge is impossible, the future appears open and undetermined. Black holes represent perhaps the most extreme environment for the physics of time. These regions of spacetime where gravity is so intense that not even light can escape push general relativity to its limits. Near the event horizon of a black hole, time dilation becomes extreme. To a distant observer, an object falling toward a black hole would appear to slow down and freeze at the horizon, never quite crossing. To the falling object itself, however, the crossing would happen in finite time. At the center of a black hole, according to general relativity, lies a singularity, a point of infinite density where the known laws of physics break down. What happens to time at a singularity is unknown. Some theories suggest that time itself ends there, that asking what happens after reaching a singularity is as meaningless as asking what is north of the North Pole. Stephen Hawking, the theoretical physicist who made groundbreaking contributions to the understanding of black holes, often pondered the nature of time. He wrote, "The increase of disorder or entropy with time is one example of what is called an arrow of time, something that distinguishes the past from the future, giving a direction to time." Hawking devoted much of his career to understanding the beginning of time at the Big Bang and the fate of time near singularities. Hawking also proposed in the 1970s that black holes are not entirely black. Through a quantum mechanical process now called Hawking radiation, black holes slowly emit particles and lose mass over time. This radiation is incredibly faint for stellar mass black holes, far too weak to detect. But it means that black holes are not eternal. Given enough time, they will evaporate completely, releasing their mass back into the universe as radiation. The timescales involved in black hole evaporation are almost incomprehensibly vast. A black hole with the mass of the Sun would take approximately 10 to the power of 67 years to evaporate. The current age of the universe, 13.8 billion years, is only about 10 to the power of 10 years. Black hole evaporation belongs to the far, far future, an epoch so distant that all the stars in the universe will have long since burned out. Contemplating such immense timescales invites a kind of cosmic perspective. The Roman philosopher Seneca advised, "It is not that we have a short time to live, but that we waste a lot of it." While human life is brief compared to the age of stars or the span of geological eras, it is vast compared to the duration of a heartbeat or the flash of a lightning bolt. Time is always relative, always dependent on the scale of comparison. The New Year moment with which this reflection began represents one particular attempt to mark time at a human scale, but other cultures and civilizations have divided time differently. The Chinese calendar, the Hebrew calendar, the Islamic calendar, the Hindu calendar, Each carries its own structure, its own rhythm, its own way of connecting human life to larger cycles. The ancient Egyptians developed one of the earliest systematic calendars based on the annual flooding of the Nile and the heliacal rising of the star Sirius. The Mayans created elaborate calendar systems with interlocking cycles of different lengths, some extending thousands of years into the past and future. The ability to track time precisely was essential for agriculture, for religious observance, for the coordination of complex societies. The invention of increasingly precise timekeeping devices marked significant advances in human capability. Sundials, which track the apparent motion of the sun across the sky, date back thousands of years. Water clocks, which measure time by the controlled flow of liquid, were used in ancient Babylon, Egypt, and China. Mechanical clocks, with their escapements and gear trains, emerged in medieval Europe and transformed the organization of daily life. The pendulum clock, perfected by the Dutch scientist Christian Huygens in 1656, represented a major leap in accuracy. Galileo had earlier recognized that a pendulum swings with a period that depends on its length, not on the size of its swing, at least for small amplitudes. This property, called isochronism, made pendulums ideal for regulating clocks. Huygens's clocks were accurate to within about 10 seconds per day, a dramatic improvement over earlier mechanisms. The need for precise time at sea drove further innovations. Determining longitude, the east-west position of a ship, requires knowing the exact time difference between the ship's location and a reference point. Without accurate portable clocks, sailors could not reliably navigate long voyages. The marine chronometer, developed by John Harrison in the 18th century, solved this problem and transformed ocean navigation. Quartz clocks, invented in the 1920s, used the piezoelectric properties of quartz crystals to keep time. When an electric current is applied to a quartz crystal, it vibrates at a precise frequency. These vibrations can be counted to measure time with far greater accuracy than mechanical clocks. Quartz technology eventually made its way into wristwatches, democratizing precise timekeeping for ordinary people. Atomic clocks, as mentioned earlier, represent the current pinnacle of timekeeping technology, but even atomic clocks face limitations. No clock can measure time with infinite precision. At the smallest scales, quantum mechanics introduces fundamental uncertainty. The very concept of time may break down at the Planck scale, approximately 10 to the power of -43 seconds, where quantum gravitational effects become important. The Planck time is the time it would take a photon traveling at the speed of light to cross a distance equal to the Planck length, about 10 to the power of -35 meters. At scales smaller than the Planck length and times shorter than the Planck time, our current theories of physics cannot make reliable predictions. Some physicists speculate the time itself may be quantized at this scale, coming in discrete units rather than flowing continuously. The relationship between time and space was revolutionized by the concept of spacetime, introduced by Hermann Minkowski shortly after Einstein published Special Relativity. Minkowski declared, "Henceforth space by itself and time by itself are doomed to fade away into mere shadows, and only a kind of union of the two will preserve an independent reality." This union, space-time, treats time as a fourth dimension intimately connected to the three dimensions of space. In the spacetime picture, events are located not just by where they occur, but by when they occur. The path of an object through spacetime is called its world line. A stationary object traces a vertical world line, advancing through time without moving through space. A moving object traces a tilted world line, advancing through both time and space. Light follows world lines at a special angle that defines the structure of causality. The light cone of an event encompasses all points in space-time that could be causally connected to that event. The past light cone contains all events that could have influenced the given event. The future light cone contains all events that the given event could influence. Events outside both light cones are causally disconnected, unable to affect or be affected by the given event through any physical process. This causal structure is preserved in special relativity. No physical influence can travel faster than light, which means the order of causally connected events is the same for all observers. If event A can cause event B, then A will precede B in every reference frame. The relativity of simultaneity means that different observers may disagree about whether distant events are simultaneous, but they cannot disagree about causal order. General relativity allows for more exotic possibilities. Solutions to Einstein's field equations have been found that permit closed time-like curves, world lines that loop back on themselves, potentially allowing travel into the past. The mathematician Kurt Gödel discovered one such solution in 1949, describing a rotating universe in which time travel would be possible. However, this universe does not appear to match observed reality. The possibility of time travel remains a subject of scientific and philosophical interest. Wormholes, hypothetical tunnels through space-time, might in principle connect distant points in both space and time. But maintaining a traversable wormhole would require exotic matter with negative energy density, which may not exist. And the paradoxes that time travel would create, such as the possibility of preventing one's own birth, suggest deep constraints that physics must respect. Stephen Hawking proposed what he called the chronology protection conjecture, suggesting that the laws of physics conspire to prevent time travel into the past. While no proof of this conjecture exists, the absence of visitors from the future and the consistency of known physics support the idea that backward time travel may be impossible. Whether or not time travel is possible, the direction of time remains one of the most fundamental features of the universe. The asymmetry between past and future shapes everything from memory to mortality, from the growth of crystals to the collapse of stars. Time's arrow points toward increasing entropy, toward the spread of energy, toward the dissolution of organized structures. Yet within this general trend toward disorder, remarkable islands of complexity have arisen. Stars form from diffuse gas clouds concentrating matter and energy. Planets coalesce from stellar debris, creating environments where chemistry can flourish. Life emerges and evolves, building increasingly sophisticated structures that capture and process energy. Consciousness arises, enabling the universe to reflect upon itself. The physicist Erwin Schrödinger, famous for his contributions to quantum mechanics, pondered how living organisms seem to defy the trend toward disorder. He suggested that life feeds on negative entropy, or negentropy, maintaining its organization by exporting entropy to its environment. A living cell is not a closed system but an open one, exchanging matter and energy with its surroundings. This perspective reveals that the apparent conflict between life and entropy is illusory. Life does not violate the second law of thermodynamics, but exploits it. By coupling internal ordering processes to external disordering processes, organisms maintain their complexity. The price of biological order is disorder elsewhere, paid in the currency of waste heat and molecular decay. The contemplation of time in the quiet aftermath of the new year leads through many territories, from the human rituals of calendar and celebration to the physics of relativity and entropy, from the biological rhythms of bodies to the cosmic scales of galaxies. Time reveals itself as endlessly multifaceted. It is the medium of all experience, the condition of all change, the framework within which all questions are asked and all answers given. The Stoic philosopher Marcus Aurelius, Roman emperor and author of the Meditations, reflected often on time and mortality. He wrote, "Time is a sort of river of passing events, and strong is its current. No sooner is a thing brought to sight than it is swept by, and another takes its place, and this too will be swept away." This image of time as a river carrying all things ceaselessly forward resonates across centuries. Yet even rivers have their origins and their ends. The Amazon begins as trickles of meltwater high in the Andes and empties into the Atlantic after a journey of thousands of kilometers. Time, too, may have an origin in the Big Bang, though what lies before remains unknown. And time may have an end in the heat death of the universe, when entropy reaches its maximum and nothing further can happen. The heat death predicted by thermodynamics represents the ultimate future of a universe governed by the second law. As entropy increases and energy spreads out, temperature differences diminish. Without temperature differences, no work can be done, no processes can occur, no changes can happen. The universe would become a vast, cold, dark expanse of uniformly distributed particles, unchanging for all eternity. This fate lies unimaginably far in the future. First, the stars must burn out, which will take trillions of years. Then the stellar remnants must cool and disperse. Then the black holes must evaporate over timescales that make the current age of the universe seem like an eye blink. Only then, in the aftermath of everything, would true equilibrium reign. The poet T.S. Eliot wrote, "Time present and time past are both perhaps present in time future and time future contained in time past." These lines from 4 quartets suggest a view of time in which all moments interpenetrate, each containing echoes and anticipations of the others. Poetry, like physics, offers glimpses into time's nature, though from a different angle of approach. In the stillness of the early hours of the new year, time continues its steady flow. The clocks tick. The earth rotates, the sun shines on the other side of the planet, its light 8 minutes old by the time it arrives. The galaxies recede from one another as space itself expands. And somewhere in the human heart, the mystery of time's passage creates the conditions for wonder, for remembrance, for hope. The French philosopher Blaise Pascal observed the strange position of human beings in the scale of things. He wrote, "Through space, the universe grasps me and swallows me up like a speck. Through thought, I grasp it." This paradox captures something essential about the human relationship to time as well. Human lives are brief sparks in the vast night of cosmic time, yet human minds can contemplate billions of years, can conceive of the birth and death of stars, can trace the unfolding of time from its earliest moments. The measurement of time has always been connected to astronomy. The day is defined by the Earth's rotation. The month originally tracked the moon's phases. The year follows the Earth's orbit around the sun. These astronomical rhythms provided the original framework for human timekeeping, and though modern clocks have become independent of astronomical observations, the connection remains in the structure of calendars. A day is not exactly 24 hours if measured against the stars rather than the sun. The sidereal day, the time for the Earth to complete one rotation relative to distant stars, is approximately 23 hours, 56 minutes, and 4 seconds. The solar day is about 4 minutes longer because the Earth must rotate slightly more than a full turn to bring the sun back to the same position in the sky, accounting for the distance traveled along its orbit. The year itself is defined in multiple ways. The tropical year used for calendars measures the time between successive vernal equinoxes. The sidereal year measures the time for the Earth to return to the same position relative to the stars. The anomalistic year measures the time between successive closest approaches to the sun. These definitions differ slightly because the Earth's orbit is not perfectly stable, but shifts gradually over millennia. Such shifts are caused by gravitational influences from other planets, particularly Jupiter, and by the precession of the Earth's rotational axis. This precession, a slow wobble like that of a spinning top, completes one cycle approximately every 26,000 years. As a result, the positions of the stars relative to the seasons gradually change over time. The star Polaris, currently close to the north celestial pole, was not the pole star in ancient times, and will not be again for thousands of years. The timescale of precession, measured in tens of thousands of years, bridges the human and the geological. It is long enough to be invisible in individual lifetimes, but short enough to have been detected by careful observation. The ancient Greek astronomer Hipparchus is credited with discovering precession around 129 BCE by comparing his star catalogs with those made by earlier observers. Beyond precession lie even slower changes. The Earth's orbital eccentricity, axial tilt, and the timing of perihelion all vary over cycles of tens to hundreds of thousands of years. These Milankovitch cycles, named after the Serbian scientist who calculated them, influence the amount and distribution of sunlight reaching Earth's surface. They are thought to be the primary driver of the ice ages that have repeatedly covered northern continents in glaciers. The last ice age ended approximately 11,700 years ago, ushering in the current interglacial period known as the Holocene. All of human civilization has developed within this relatively stable and warm climatic window. Agricultural societies, cities, writing, science, everything that characterizes human history as we know it emerged within this geological instant. The geologist and author John McPhee, in his writings on deep time, used the image of the human arm to convey the scale of Earth's history. If the Earth's history were represented by the length of an arm from shoulder to fingertip, a single stroke of a nail file would remove all of human history. This image captures the humbling perspective that geology provides. Yet within that fingernail scraping, within that sliver of time, human consciousness has awakened to the vast spans that preceded it. The ability to conceive of deep time, to imagine millions and billions of years, is itself a remarkable development in the history of the universe. Matter has organized itself into forms that can contemplate their own temporal origins and likely destinations. The biochemist and writer J.B.S. Haldane suggested, the universe is not only queerer than we suppose, but queerer than we can suppose. Time may be one of those aspects of reality that exceeds human conceptual capacity. The intuitions shaped by everyday experience, where time flows uniformly and predictably, may be inadequate guides to time's true nature at extreme scales and speeds. In quantum mechanics, time plays a peculiar role. Unlike position and momentum, which are represented by operators and can be measured with associated uncertainties, time in standard quantum mechanics is a classical parameter. The Schrödinger equation describes how quantum states evolve in time, but time itself is not quantized in the usual formulation. This asymmetric treatment of time has puzzled physicists and suggests that something fundamental may be missing from current theories. The Wheeler-DeWitt equation, an attempt to combine quantum mechanics with general relativity, contains no explicit time variable. This has led some physicists to propose that time is emergent rather than fundamental, arising from more basic timeless relations. In this view, the universe as a whole exists timelessly, and what we call the flow of time is a consequence of our perspective as observers embedded within it. The physicist Julian Barber has developed this idea extensively, arguing that time is an illusion and that reality consists of static configurations of the universe, which he calls nows. What we experience as time's passage would be a psychological phenomenon arising from the way these nows are related to one another through records and correlations. It is a challenging idea, difficult to reconcile with the vivid sense of temporal flow. The debate between those who see time as fundamentally real and those who see it as derivative or illusory continues. Both camps can point to aspects of physics and experience that support their views. The resolution, if one comes, may require new physics that transcends current theories, perhaps a successful theory of quantum gravity that explains how space-time emerges from more fundamental structures. Whatever the ultimate nature of time, its role in human experience remains central and inescapable. Every thought, every perception, every action unfolds in time. Memory reaches backward, anticipation reaches forward, and attention illuminates the present moment as it passes. Consciousness is inherently temporal, a process rather than a thing, a verb rather than a noun. The philosopher William James, brother of the novelist Henry James, studied the psychology of time perception in the late 19th century. He introduced the concept of the specious present, the duration of time that is experienced as now rather than as past or future. Research suggests this present moment has a span of roughly 2 to 3 seconds, within which events are perceived as simultaneous and unified. Beyond this specious present, events are organized by memory and anticipation into temporal sequences. The sense of personal identity depends on this temporal organization, on the ability to connect present experience to past memories and future plans. Damage to certain brain regions can disrupt this temporal coherence, leaving individuals trapped in a permanent present without access to personal history or ability to imagine the future. The novelist Marcel Proust explored the relationship between time and memory in his masterwork In Search of Lost Time. The famous episode of the Madeleine, in which a taste triggers a flood of childhood memories, illustrates how sensory experience can bypass ordinary remembering and reconnect consciousness with the past. Proust wrote, "The past is hidden somewhere outside the realm, beyond the reach of intellect, in some material object which we do not suspect." Such involuntary memories reveal that the past is not simply gone, but remains encoded in the body and brain, ready to resurface under the right conditions. The smell of a particular flower, the sound of a certain song, the quality of afternoon light, any of these can serve as a key to unlock temporal vaults. Time, in this sense, is layered within experience, present moments containing echoes of past ones. As the night deepens and the new year grows older by the hour, the rhythms of time continue at every scale. Atoms vibrate, cells divide, heartbeats mark their steady interval. The Earth turns toward dawn. The solar system orbits the galactic center, a journey taking approximately 230 million years to complete. The galaxy itself drifts through the expanding universe, carried by the stretching of space. In the structure of space-time, past, present, and future are woven together into a single fabric. Whether this fabric is static or genuinely flowing, whether time is fundamental or emergent, whether the future is open or determined, these questions may never receive final answers accessible to human understanding. But the contemplation of such questions is itself a form of participation in time's mystery. The stars visible in the night sky span a range of ages and distances. Some are young, recently ignited, their nuclear fires just beginning. Others are ancient, nearing the end of their fuel supplies, preparing for transformation into white dwarfs, neutron stars, or black holes. The light from each carries information about its source, a message transmitted across time as well as space. The Hubble Space Telescope and its successor, the James Webb Space Telescope, have extended human vision to galaxies billions of light years away, galaxies as they appeared billions of years in the past. These observations reveal that the universe has changed dramatically over cosmic time. Early galaxies were smaller, bluer, and more chaotic than the grand spiral and elliptical galaxies of the present epoch. Time has sculpted the cosmic landscape. The expansion of the universe means that distant galaxies are receding from us, and the more distant they are, the faster they recede. Beyond a certain distance, called the cosmic event horizon, galaxies are receding faster than light can travel toward us. Light from these regions will never reach Earth, no matter how long the universe continues. The observable universe is bounded by this horizon, a temporal as well as spatial limit. The discovery that the universe's expansion is accelerating, announced in 1998 based on observations of distant supernovae, added another dimension to cosmic time. Dark energy, the mysterious force driving this acceleration, will gradually push more and more galaxies beyond the cosmic horizon. In the far future, observers in our galaxy would see an increasingly empty sky, with other galaxies fading from view as they cross the horizon. This ultimate isolation lies trillions of years in the future, long after the sun has died and the Earth has been consumed. But it illustrates how the structure of time at cosmic scales differs from everyday intuition. The future of the universe is not simply more of the same, but a progression toward states qualitatively different from the present. The writer Jorge Luis Borges frequently explored time in his fiction and essays. In The Garden of Forking Paths, he imagined a novel that included all possible outcomes of every decision, creating a labyrinthine network of branching timelines. Borges wrote, "Time forks perpetually toward innumerable futures." This image resonates with interpretations of quantum mechanics that posit multiple parallel worlds. The many worlds interpretation proposed by Hugh Everett in 1957 suggests that every quantum measurement causes the universe to branch into multiple versions, each realizing a different outcome. In this view, time does not fork toward one future, but toward all possible futures simultaneously. What we experience as a single timeline would be just one branch among an unimaginably vast tree. Whether this interpretation captures reality or merely offers a mathematical convenience remains debated, but it illustrates the range of possibilities that physics permits. Time may be far stranger than ordinary experience suggests, and the simple image of a single past flowing into a single future may be a drastic simplification. The night continues its passage. Stars wheel slowly across the sky, their apparent motion reflecting the Earth's rotation. The moon, if visible, shows a phase determined by its position relative to the sun, a cycle that will complete in about 29.5 days. The planets pursue their own orbits, some faster, some slower than Earth, creating the complex dance observed since ancient times. The measurement of planetary motion led Johannes Kepler to discover in the early 17th century that planets move in ellipses rather than circles, with the sun at one focus. His three laws of planetary motion, formulated between 1609 and 1609, provided the foundation for Newton's later synthesis. Kepler's work demonstrated that precise measurement and mathematical analysis could reveal the hidden order of celestial time. Newton's law of universal gravitation, published in 1687, explained Kepler's laws as consequences of a single mathematical principle. It predicted the motions of planets, moons, and comets with unprecedented accuracy. For over 2 centuries, Newtonian mechanics reigned supreme, its conception of absolute time unchallenged. Only with Einstein's revolution did the limitations of this framework become apparent. Yet Newtonian physics remains an excellent approximation for everyday purposes. The relativistic corrections to time are negligible at ordinary speeds and gravitational fields. The bridge between Newton and Einstein illustrates how scientific understanding deepens over time, with new theories encompassing and extending older ones, rather than simply replacing them. The concept of a paradigm shift, introduced by the historian and philosopher of science Thomas Kuhn, describes how scientific revolutions transform not just specific theories, but entire frameworks of understanding. Einstein's relativity represented such a shift, changing not just the equations of physics, but the fundamental concepts of space and time. Future shifts may yet occur, revealing aspects of time currently invisible. For now, the clocks continue their reliable measurement. The atomic clocks in laboratories around the world maintain the international standard of Coordinated Universal Time, abbreviated UTC. This standard is based on atomic time, but is adjusted with occasional leap seconds to stay synchronized with the Earth's slightly irregular rotation. The most recent leap second was added in 2016, and discussions continue about whether to abolish the practice. Leap seconds arise because the Earth's rotation is gradually slowing due to tidal friction from the Moon. Each century, the day lengthens by approximately 1.4 milliseconds. This may seem negligible, but over millions of years, the effect is substantial. 600 million years ago, the day was only about 21 hours long. In the distant future, if the Earth-Moon system continues to exist, the day will lengthen further still. The tidal interaction also causes the Moon to slowly recede from Earth at a current rate of about 3.8 centimeters per year. Eventually, in billions of years, the Moon will appear smaller in the sky than it does today. Total solar eclipses, in which the Moon precisely covers the Sun, will become impossible as the apparent size of the Moon shrinks below that of the Sun. Eclipses have marked significant moments in human history. Ancient peoples often interpreted them as omens or divine signs. The prediction of eclipses became one of the triumphs of mathematical astronomy, demonstrating that celestial events followed regular patterns accessible to reason. Today, eclipse paths can be predicted centuries in advance with perfect accuracy. The Greek philosopher Thales is traditionally credited with predicting a solar eclipse in 585 BCE, though the details remain uncertain. Whether or not the specific attribution is accurate, the story reflects the ancient aspiration to understand time's regularities, to see through the apparent chaos of events to the underlying order. This same aspiration continues in modern physics, where scientists seek theories that encompass all observations and predict future phenomena. The quest for a theory of everything, uniting quantum mechanics and general relativity, is in part a quest to understand time at its most fundamental level. Such a theory might reveal whether time is truly fundamental or emerges from timeless foundations. The pursuit of knowledge about time is itself a temporal process, unfolding over generations. Each generation builds upon the work of predecessors, correcting errors, extending insights, opening new questions. The scientific enterprise is a collective activity spread across time, a conversation that spans centuries and continents. The astronomer Edwin Hubble, who in the 1920s demonstrated that the universe extends far beyond our galaxy and is expanding, contributed fundamentally to the understanding of cosmic time. Before Hubble, the nature and scale of the universe were unknown. After Hubble, humanity knew that it inhabited one galaxy among billions, in a universe billions of years old and billions of light years across. This expansion of cosmic perspective paralleled an expansion of temporal perspective. The universe was not static and eternal, but dynamic and evolving. It had a beginning and would have a future different from its past. Cosmology became a historical science, tracing the development of the universe from its fiery origin to its unknown destiny. The night passes, as all nights do, carrying the first hours of the new year into memory. The clocks that marked midnight continue their patient counting. Each second is identical to every other second in the metric of time, yet each second is unique in the events it contains. The tension between these perspectives, time as measure and time as experience, persists through all attempts at resolution. Perhaps this tension is not a problem to be solved, but a reality to be acknowledged. Time in its fullness may encompass both the physicist's equations and the poet's intuitions, the clock's precision and the heart's rhythm. The multiple facets of time, physical, biological, psychological, cultural, may be aspects of a single phenomenon too rich for any single perspective to capture. In the words of the physicist John Wheeler, who made foundational contributions to general relativity and quantum mechanics, time is what prevents everything from happening at once. This humorous observation points to a deep truth. Time is the framework that allows sequence, allows causation, allows the unfolding of stories. Without time, there would be no before and after, no change, no process, no life. The presence of time makes the universe historical. It makes stories possible, not just human stories, but the story of the cosmos itself, from Big Bang to heat death, from primordial plasma to stars and planets and life and minds. Each moment is a chapter in this vast narrative. Each event a word in a sentence, too long for any reader to comprehend entire. The contemplation of time in the stillness of a new year's beginning is itself part of this story. Consciousness reflecting on its temporal nature is a development billions of years in the making. The atoms in human bodies were forged in ancient stars, scattered by supernovae, gathered into planets, incorporated into organisms, and eventually arranged into patterns capable of wondering about time. Carl Sagan expressed this idea memorably. We are a way for the cosmos to know itself. Through human consciousness, time has become aware of itself. The same temporal processes that govern the evolution of galaxies and the decay of radioactive atoms also operate in brains that contemplate these processes. The observer and the observed are woven from the same temporal fabric. As this reflection approaches its midpoint, the themes introduced at the beginning resonate still. The clock striking midnight, the year turning, the human rituals of time measurement and celebration all participate in larger patterns that extend from the subatomic to the cosmic. Time is one, though its manifestations are many. The second hand's sweep and the galaxy's rotation are expressions of the same underlying reality. The coming hours will bring dawn, the Earth's rotation carrying its nightward face toward the sun. Light will spread across landscapes, warming air and awakening creatures. The daily cycle will continue, as it has for billions of years, providing the rhythm against which life has evolved. Morning is not far off, and with it, the new year's first day will fully begin. But for now, the night holds its depth. Stars shine above clouds or clear skies, their light ancient and steady. The moon pursues its orbit. Somewhere, a clock ticks, marking intervals too brief to feel, yet accumulating into hours, days, years, lifetimes. Time flows on, as it always has, as it always will, bearing all things forward into whatever comes next. The universe expands in silence, across distances that light itself requires billions of years to traverse. Galaxies drift apart from one another, carried by the stretching of space. This expansion was discovered through the redshift of distant light, a lengthening of wavelengths that reveals the motion of recession. The farther a galaxy lies, the faster it appears to flee. Not because galaxies are moving through space, but because the space between them is growing. This cosmic expansion provides one of the clearest arrows of time in physics. In the past, the universe was smaller, denser, hotter. In the future, it will be larger, sparser, colder. Running the film of cosmic history backward leads inevitably to the Big Bang, that moment of extreme density from which everything emerged. Running it forward leads toward the vast, cold emptiness of maximal entropy. The temperature of the cosmic microwave background radiation, currently about 2.7 Kelvin, provides a measure of the universe's age. This radiation has been cooling since its emission 380,000 years after the Big Bang, and its temperature decreases as the universe expands. In the far future, as expansion continues, the background temperature will approach absolute zero, the cessation of all thermal motion. Absolute zero, approximately minus 273.15 degrees Celsius or 0 Kelvin, represents a limit that can be approached but never quite reached. The third law of thermodynamics states that the entropy of a perfect crystal approaches zero as temperature approaches absolute zero, but reaching zero temperature exactly would require infinite steps. Even in the coldest reaches of interstellar space, temperatures remain slightly above this absolute floor. The coldest known natural place in the universe is the Boomerang Nebula, a planetary nebula about 5,000 light-years from Earth, where temperatures drop to about 1 Kelvin. This extreme cold results from the rapid expansion of gas ejected by a dying star. In laboratories, scientists have achieved temperatures within billionths of a degree of absolute zero, creating exotic states of matter that reveal quantum effects at macroscopic scales. At such extreme temperatures, the distinction between different quantum states becomes delicate. Bose-Einstein condensates, first created in 1995, occur when bosons are cooled to temperatures so low that they all fall into the same quantum state, behaving as a single quantum entity. Time for these particles enters a strange regime where quantum coherence extends across macroscopic distances. The study of extreme conditions, whether extreme cold, extreme heat, extreme gravity, or extreme speeds, has repeatedly revealed that time behaves differently than everyday experience suggests. Each extreme pushes against the boundaries of classical intuition, revealing the more fundamental physics that underlies ordinary appearances. Near the surface of a neutron star, the collapsed remnant of a massive star's core, gravity is so intense that time runs noticeably slower than far away. A neutron star packs more than the sun's mass into a sphere, perhaps 20 kilometers across. The gravitational time dilation at its surface is significant, slowing time by roughly 30% compared to distant regions. Such objects were purely theoretical until the 1960s when pulsars were discovered. Pulsars are rapidly rotating neutron stars that emit beams of radiation like cosmic lighthouses. Some pulsars rotate hundreds of times per second, their surfaces moving at significant fractions of the speed of light. The precise timing of pulsar signals has become a tool for testing physics, including the detection of gravitational waves. The stability of pulsar timing is so remarkable that some pulsars rival atomic clocks in their regularity. Millisecond pulsars, which have been spun up by accreting matter from companion stars, tick with periods stable to within a microsecond over years of observation. This stability makes them natural timekeepers scattered throughout the galaxy, their signals carrying information about the spacetime through which they travel. Gravitational waves, ripples in the fabric of spacetime itself, were predicted by Einstein in 1916, but not directly detected until 2015 by the LIGO experiment. These waves are produced by accelerating masses, particularly by cataclysmic events such as the merger of two black holes or two neutron stars. As gravitational waves pass through space, they alternately stretch and compress distances, including the lengths of the detector arms that measured them. The detection of gravitational waves opened a new window on the universe, allowing observation of events that emit little or no light. The merger of two black holes, for instance, produces no electromagnetic radiation, but releases enormous energy in gravitational waves. These events offer insights into some of the most extreme environments where time and space are most severely distorted. The first gravitational wave signal detected, designated GW150914, came from two black holes merging about 1.3 billion light-years away. The event released more energy than all the stars in the observable universe combined. Yet by the time the waves reached Earth, they had spread so thin that they stretched the 4-kilometer detector arms by less than 1,000th of the diameter of a proton. Detecting such infinitesimal changes required extraordinary precision. The physicist Kip Thorne, one of the pioneers of gravitational wave research, spent decades developing the theoretical and experimental foundations for detection. He observed, "The warping of space and time is a wonderful thing to contemplate. This warping, central to general relativity, means that the geometry of the universe is dynamic, shaped by the matter and energy within it, and that this shaping includes the dimension of time. The geometry of spacetime near a rotating black hole was worked out by the mathematician Roy Kerr in 1963. Kerr's solution revealed that rotation drags spacetime around with it, an effect called frame dragging. Near a rapidly spinning black hole, this dragging is so severe that nothing can remain stationary relative to distant stars. Even light must rotate with the black hole's spin. The region around a rotating black hole where frame dragging becomes inescapable is called the ergosphere. Within this region, an object can extract energy from the black hole's rotation through a process called the Penrose process, named after the physicist Roger Penrose who proposed it. This extraction reduces the black hole's spin, converting rotational energy into the energy of particles escaping to infinity. Roger Penrose also made fundamental contributions to understanding singularities and the nature of time in general relativity. His singularity theorems, developed with Stephen Hawking in the 1960s and 1970s, proved that under very general conditions, singularities are inevitable in gravitational collapse and at the Big Bang. These results showed that the equations of general relativity predict their own breakdown, pointing toward the need for a quantum theory of gravity. Penrose has also proposed controversial ideas about the role of consciousness in quantum mechanics and the possibility that consciousness might involve quantum processes in the brain. He suggested consciousness is not merely the result of complex computation, but involves something fundamentally new. Whether or not these ideas prove correct, they illustrate the deep connections that some thinkers perceive between the mysteries of time, quantum mechanics, and the mind. The relationship between quantum mechanics and time remains one of the most puzzling aspects of modern physics. In the standard formulation, the Schrödinger equation describes how quantum states evolve smoothly and deterministically in time. But when a measurement is made, the quantum state appears to collapse suddenly and probabilistically to one of the possible outcomes. This measurement problem has generated decades of debate about the foundations of quantum mechanics. Some interpretations, like the many worlds view mentioned earlier, avoid collapse by proposing that all outcomes occur in different branches of reality. Others, like the Copenhagen interpretation, accept collapse as fundamental but refrain from specifying exactly when or how it occurs. Still others, like the pilot wave theory, restore determinism by adding hidden variables. None has achieved universal acceptance, and the nature of quantum measurement remains contested. The physicist John Bell demonstrated in 1964 that no theory based on local hidden variables could reproduce all the predictions of quantum mechanics. Bell's theorem and subsequent experimental tests have confirmed that quantum correlations exhibit a form of non-locality with entangled particles showing correlations that cannot be explained by any local mechanism. These correlations do not allow faster than light signaling, but they do suggest that quantum reality is deeply interconnected across space. Whether quantum non-locality implies something about the nature of time remains unclear. In the block universe picture favored by some interpretations of relativity, all events already exist in a timeless four-dimensional manifold, and quantum correlations simply reflect the structure of this manifold. In other views, quantum measurements create new facts about reality, and time is genuinely open and creative. The philosopher Alfred North Whitehead proposed a process philosophy in which reality consists not of static substances but of events or occasions of experience. In this view, time is fundamental, and each moment involves a creative advance into novelty. Whitehead wrote, "The present contains all that there is. It is holy ground, for it is the past and it is the future." This perspective resonates with those who see time as genuinely flowing rather than merely appearing to flow. The experience of time flowing is universal among humans, though its intensity varies. In states of deep absorption, sometimes called flow states, the sense of time passing may fade or disappear. In states of anxiety or boredom, time may seem to drag interminably. Altered states of consciousness induced by meditation, dreams, or certain substances can radically transform temporal experience. Studies of meditators have shown that experienced practitioners can develop unusual relationships with time. Some report a sense of timelessness during deep meditation, a state in which the present moment seems to expand and the ordinary sense of duration dissolves. Neuroscientific research has identified changes in brain activity associated with these states, though much remains to be understood. The experience of time in dreams offers another window into the mind's temporal flexibility. Dreams can compress long, apparent durations into brief periods of sleep, or expand moments into seemingly endless sequences. The sense of temporal order in dreams is often disrupted, with events occurring in scrambled sequences or without clear causal connections. Upon waking, the dream narrative may reorganize itself into a more coherent timeline, suggesting that temporal order is partly constructed by waking consciousness. The neuroscientist David Eagleman has studied time perception extensively. He notes, "Time is not simply a measure of the movement of celestial bodies. It is a construction of the brain. This construction involves multiple neural systems that track different aspects of temporal experience, from the millisecond timing needed for speech and motor control to the longer timescales of memory and planning." Damage to specific brain regions can produce striking disturbances in time perception. Patients with certain types of brain injury may lose the ability to perceive the temporal order of events, even while still perceiving the events themselves. Others may experience time as moving abnormally fast or slow. These clinical cases reveal that the seamless sense of temporal flow depends on the intact functioning of particular neural circuits. The neurotransmitter dopamine appears to play a significant role in time perception. Conditions that affect dopamine levels, such as Parkinson's disease or the use of certain drugs, can alter the subjective sense of time's passage. This suggests that the brain's internal clock is chemically regulated and can be adjusted by pharmacological interventions. Body temperature also influences time perception in measurable ways. When body temperature rises, the internal clock speeds up, making external time seem to pass more slowly. When body temperature falls, the internal clock slows, making external time seem to speed up. This relationship suggests that time perception is tied to metabolic processes, to the rate at which the body consumes energy and processes information. Aging also affects time perception in characteristic ways. Older adults often report that time seems to pass more quickly than it did in youth. Several explanations have been proposed for this phenomenon. One suggests that as the proportion of novel experiences decreases with age, fewer distinct memories are formed, making each year seem shorter in retrospect. Another points to changes in metabolic rate and neural processing speed that might alter the brain's internal clock. The philosopher and psychologist William James discussed this phenomenon in the 19th century. He wrote, "The same space of time seems shorter as we grow older. In youth, we may have an absolutely new experience, subjective or objective, every hour of the day. Each such experience, however, gives us a perception of the interval during which it occurred. This connection between novelty and temporal duration remains a key insight in understanding subjective time." Memory's role in constructing the experience of time extends beyond the moment of experience to the later recollection. Events that were rich in detail and emotion tend to be remembered as lasting longer than events that were impoverished or unremarkable. This retrospective construction of duration means that how time is remembered may differ significantly from how it was experienced in the moment. The holiday paradox illustrates this distinction. A vacation filled with new experiences may seem to fly by in the moment, as attention is fully absorbed in the present. But in retrospect, the same vacation may be remembered as long and rich, because many distinct memories were formed. Conversely, a monotonous week at home may drag in the moment but later seem to have passed quickly, leaving few memories to mark its duration. These observations suggest that there may be no single answer to the question of how long an experience lasted. Duration as lived and duration as remembered are distinct dimensions of temporal experience, each constructed by different processes and subject to different biases. The truth about time, at least for conscious beings, is irreducibly plural. The night continues its slow progress toward morning. In the eastern sky, the first faint hints of dawn may begin to appear, a gradual lightening that signals the approach of the sun. The Earth's rotation, carrying observers toward the day, proceeds with perfect regularity, unaffected by human concerns or cosmic contemplations. The regularity of the Earth's rotation was once the standard by which time was measured, Before atomic clocks, the length of the day defined the second, with each day divided into 86,400 equal parts. But the Earth's rotation is not perfectly uniform. It is slowed by tidal friction and perturbed by geological processes, atmospheric movements, and even the redistribution of mass as ice sheets melt. These variations in Earth's rotation are tracked by precise measurements and corrections. The difference between atomic time and Earth rotation time is reconciled through the leap seconds mentioned earlier, ensuring that clocks remain synchronized with the sun's position in the sky. This synchronization is important for navigation, telecommunications, and the coordination of global activities. The distinction between atomic time and rotational time illustrates how human timekeeping has evolved from astronomical observation to physical measurement. The second is no longer defined by the Earth's motion, but by the behavior of cesium atoms. Yet the cycles of day and night, season and year remain fundamental to human life and cannot be abandoned entirely. Cultural time, the shared temporal framework within which societies operate, is built upon these natural cycles, but elaborated in countless ways. Work schedules, holidays, rituals, and commemorations create a social temporality that varies across cultures and eras. The 7-day week, for example, has no astronomical basis but has become nearly universal, its origins tracing back to ancient Mesopotamia and biblical traditions. The naming of days and months preserves traces of ancient religious and cultural associations. Thursday derives from Thor's day, Friday from Freya's day, Saturday from Saturn's day. January takes its name from Janus, the Roman god of beginnings and transitions, appropriately placed at the start of the calendar year. These names connect the present to distant pasts, linguistic fossils embedded in everyday speech. The standardization of time zones is a relatively recent development necessitated by the spread of railroads and telecommunications in the 19th century. Before time zones, each locality kept its own time based on the sun's position. But when trains needed to run on schedules and telegraphs needed to coordinate messages, a unified system became essential. The prime meridian at Greenwich, England, was established as the reference for global time in 1884. Coordinated Universal Time, the successor to Greenwich Mean Time, now serves as the global standard. It is broadcast by radio signals and satellite systems, allowing clocks worldwide to synchronize to common reference. This coordination underlies the functioning of modern infrastructure, from power grids to financial markets to the internet. The precision of modern timekeeping enables technologies that would have seemed magical to earlier generations. High-frequency trading in financial markets executes transactions in microseconds, faster than human perception. Scientific experiments synchronize events across continents with nanosecond accuracy. Spacecraft navigate to distant planets using timing signals that must account for relativistic effects. The physicist and science popularizer Neil deGrasse Tyson has noted, "The universe is under no obligation to make sense to you." This observation applies well to time, which defies common sense at both small and large scales. The intuitions formed by everyday experience provide poor guides to the physics of time dilation, the psychology of time perception, or the cosmology of time's beginning and possible end. Yet despite its strangeness, time remains accessible to investigation. The scientific method applied over centuries has gradually revealed time's properties through observation, hypothesis, and experiment. From the pendulum clocks of Galileo and Huygens to the atomic clocks of the present day, From the philosophical puzzles of Augustine to the physical theories of Einstein, understanding has deepened even as mystery has remained. The physicist and philosopher Ernst Mach, whose ideas influenced Einstein, advocated for a relational view of time in which time has no existence independent of the events and processes that occur within it. Mach wrote, "It is utterly beyond our power to measure the changes of things by time. Quite the contrary, time is an abstraction at which we arrive by means of the changes of things." This perspective anticipates some modern approaches that seek to explain time in terms of more fundamental timeless structures. The debate between relational and absolute conceptions of time stretches back through the history of philosophy. Leibniz argued against Newton's absolute time, proposing instead that time is nothing but the order of successive events. Newton insisted that absolute time was necessary to make sense of his laws of motion. Einstein's relativity vindicated aspects of both views, showing that time is neither purely absolute nor purely relational, but space-time relative. The development of physics continues, and with it, the understanding of time may yet be transformed again. String theory, loop quantum gravity, and other approaches to quantum gravity propose structures from which space-time might emerge. In these speculative frameworks, the familiar time of everyday experience would be an approximation valid at large scales, like the smoothness of water emerging from the quantum behavior of molecules. The theoretical physicist Lee Smolin has argued that time is real and fundamental, contrary to views that see it as emergent or illusory. He suggests, nothing we know or experience gets closer to the heart of nature than the flow of time. Whether Smolin's perspective will gain acceptance depends on future developments in physics and philosophy, developments that will themselves unfold in time. The contemplation of time leads naturally to reflections on mortality. Every living thing exists within time, growing, changing, and eventually dying. The awareness of mortality, which seems unique to humans among animals, shapes culture, religion, art, and philosophy. The knowledge that time runs out gives urgency to life and meaning to its moments. The ancient Greek philosopher Heraclitus contemplated the relationship between time and change over 2 millennia ago. He famously observed that one cannot step into the same river twice, for the waters are ever flowing. This insight captures the ceaseless flux of temporal existence, the way that nothing remains static, the way that each moment brings transformation. Heraclitus also suggested that fire, with its constant motion and transformation, was the fundamental element of reality. This image of reality as process rather than substance anticipates modern physics, where matter is revealed as patterns of energy, and even apparently solid objects are composed of particles in constant motion. The Stoic philosophers of ancient Rome made the contemplation of mortality a central practice. Seneca counseled, "Let us prepare our minds as if we'd come to the very end of life. Let us postpone nothing. Let us balance life's books each day." This advice was not morbid but liberating, intended to free the mind from trivial concerns and focus attention on what truly matters. Marcus Aurelius, mentioned earlier, also meditated frequently on the transience of all things. He wrote in his private journal, "Think of yourself as dead. You have lived your life. Now take what's left and live it properly." For the Stoics, the awareness of time's passage was inseparable from the practice of philosophy, which aimed at living wisely and well. Different cultures have developed different relationships with mortality and time. Some emphasize the importance of this life, urging attention to the present moment. Others focus on life after death, seeing earthly time as preparation for eternity. Still others embrace cyclical views, with time repeating in eternal recurrence or souls reincarnating across multiple lives. The philosopher Friedrich Nietzsche explored the concept of eternal recurrence, the idea that time might repeat in an infinite cycle, with every moment recurring exactly as before. He proposed this idea not as a cosmological theory, but as a thought experiment. If one's life were to repeat infinitely exactly the same in every detail, would one embrace it or despair? The answer revealed one's relationship to existence. Nietzsche wrote, "What if a demon were to creep after you one night in your loneliest loneliness and say, 'This life which you now live must be lived by you once more and innumerable times more'? Would you throw yourself down and gnash your teeth and curse that demon? Or would you answer, 'You are a god, and never have I heard anything more divine'?" This thought experiment uses time to probe the depths of affirmation and despair. Whether time is linear or cyclical, the experience of its passage remains universal. Each moment arises, persists briefly, and passes into memory. The present continually advances, transforming the future into the past. This structure of experience is the foundation upon which all other aspects of time are built. The nature of the present moment has puzzled philosophers for millennia. Augustine's question returns: if the present is merely a boundary between past and future, having no duration of its own, how can it be real? And if it has duration, must it not be divisible into past and future parts? These paradoxes of the instant suggest that time's structure may be more complex than simple intuition suggests. The ancient Greek philosopher Zeno of Elea proposed famous paradoxes that challenged the common understanding of motion and time. In the paradox of Achilles and the tortoise, the swift runner can never overtake the slow crawler, because each time Achilles reaches where the tortoise was, the tortoise has moved slightly ahead. The paradox is resolved by recognizing that an infinite series of decreasing intervals can sum to a finite value, but the puzzle reveals the subtlety of continuous time. Modern physics offers no simple resolution to these philosophical puzzles. The equations of physics do not include a privileged present moment advancing through time. They describe relationships between events but do not specify which event is occurring now. The present moment, so vivid in experience, appears to have no special status in the mathematical description of nature. This discrepancy between experience and physics remains one of the deepest puzzles in the philosophy of time. Either experience is somehow illusory and there is no objective present, or physics is incomplete and something important about time remains to be discovered. Both possibilities have their defenders, and the debate continues. The writer Alan Watts, who brought Eastern philosophy to Western audiences, offered a different perspective on time. He suggested, the meaning of life is just to be alive. It is so plain and so obvious and so simple, and yet everybody rushes around in a great panic as if it were necessary to achieve something beyond themselves. This view shifts attention from time's passage to the quality of presence within each moment. Eastern traditions, particularly Buddhism and Taoism, have developed sophisticated analyses of time and its relationship to suffering. The Buddhist teaching emphasizes impermanence, the recognition that all conditioned phenomena are transient. Attachment to things that must pass leads to suffering. Freedom comes from accepting change and resting in the present moment. The Zen master Dogen wrote extensively about time in the 13th century. He proposed that time and being are inseparable, that to exist is to exist in time. He observed, "Time is not separate from you, and as you are present, time does not go away." This teaching points toward an intimate identity between the experiencing subject and the time in which experience unfolds. As the night deepens toward its darkest hour and then begins to lighten, the themes of time's contemplation weave together. The physical time of clocks and cosmos, the biological time of bodies and evolution, the psychological time of memory and anticipation, the cultural time of calendars and commemorations, all these dimensions intersect in the human experience of temporal existence. The turning of the year, the occasion that began this reflection, returns to awareness. The new year is a cultural construct, arbitrary in its timing, yet powerful in its symbolism. It offers an opportunity to pause, to look back, and to look forward. It invites reflection on what has been and imagination of what might be. The American writer F. Scott Fitzgerald captured something of time's poignancy in his work. He wrote, "So we beat on, boats against the current, borne back ceaselessly into the past." This image of striving against time's flow, while being carried by it nonetheless, resonates with the human condition. Efforts to move forward are shaped by histories that cannot be escaped. Yet time also offers possibility. Each moment is a new beginning, a chance to act differently, to learn from the past without being imprisoned by it. The arrow of time that points toward entropy and dissolution also points toward the emergence of the genuinely new. Stars form from primordial hydrogen. Life arises from chemistry. Consciousness emerges from neurons. Time creates as well as destroys. The physicist David Bohm, known for his work on quantum mechanics and philosophy, proposed that reality unfolds from a deeper implicate order. He suggested that what we perceive as separate events in time are like waves arising from an underlying ocean, manifestations of a deeper unity. In this view, time is real but derivative, an expression of more fundamental processes. Whether time is fundamental or emergent, whether it flows or only appears to flow, whether the future is open or determined, these questions remain alive. What is certain is that human existence is temporal, through and through. To be human is to be born, to grow, to age, and to die. It is to remember and to hope, to regret and to plan. It is to exist in time. The Earth continues its rotation, carrying continents toward the sun. The planet's orbit continues its circuit, marking another year in the journey around the star. The solar system continues its path through the galaxy, one circuit taking roughly 230 million years. The galaxy itself moves within the local group, part of a larger cosmic dance that stretches across billions of light years. At every scale, time is present. The half-life of a radioactive atom measures time at the quantum level. The pulse of a heart measures time at the biological level. The ring of a tree measures time at the ecological level. The layer of sediment measures time at the geological level. the light from a distant quasar, measures time at the cosmological level. The interweaving of these timescales is one of the wonders of existence. The carbon atoms in human bodies were formed in stars that lived and died billions of years ago. The genetic code that guides human development evolved over billions of years. The culture that shapes human thought emerged over thousands of years. The individual consciousness that contemplates all this spans only decades. The astrophysicist Martin Rees has reflected on humanity's place in cosmic time. He notes, "We are in some sense the waste products of ancient stars." But this cosmic perspective should not make us feel insignificant. Rather, it should be ennobling. The vastness of cosmic time does not diminish human significance, but contextualizes it, placing human existence within a larger story. The story is not finished. The universe has existed for nearly 14 billion years, but it may continue for trillions of years more. What forms consciousness might take in that immense future cannot be imagined. Human civilization, in its current form, is vanishingly brief against the backdrop of cosmic time. Yet it is within this brief moment that meaning and value exist, at least as far as is known. The philosopher Bertrand Russell, though often skeptical of metaphysics, wrote movingly about humanity's position in time. He observed, "Brief and powerless is man's life. On him and all his race, the slow, sure doom falls pitiless and dark." Yet he also found in this recognition a source of nobility, calling for the free man's worship that finds meaning not despite transience, but within it. The quiet hours of the new year offer space for such reflections. The celebrations have ended, the fireworks have faded, the champagne has gone flat. What remains is the steady passage of time marked by clocks, felt in consciousness, extending toward an unknown future. This passage is not something that happens to life, but the very medium in which life unfolds. The Roman poet Ovid wrote of time's relentless flow. He observed, "Time glides by with constant movement, not unlike a river, for neither can a river nor a light hour halt, but as wave is pushed on by wave, and as each wave as it comes is both pressed forward, and itself presses on the one in front, so time both flies and follows, and is always new." This image of time as a river has appeared throughout history, capturing something true about temporal experience. Yet time is also unlike a river in important ways. A river flows through a landscape that itself remains relatively fixed. Time has no external landscape through which it flows. Events do not pass from future to present to past like boats floating downstream. Rather, the present is always and only now, and what changes is which events occupy that present. These conceptual difficulties suggest that time is not easily captured by any single metaphor. It is like a river, like a moving spotlight, like an expanding block, like the pages of a book being written. Each metaphor illuminates some aspect while obscuring others. Perhaps time is simply too fundamental to be reduced to anything more basic. The mystery of time remains. Despite all the advances of science and philosophy, time keeps its secrets. The physicist Richard Feynman, who contributed so much to understanding quantum mechanics, remained humble about time. He confessed, "Time is a mystery that does not let itself be solved. It remains a constant query." This humility is appropriate in the face of time's depth. As dawn approaches, the sky begins to lighten imperceptibly. The stars fade, their light overwhelmed by the growing glow of the approaching sun. The constellations, which have wheeled slowly across the night sky, sink toward the western horizon. The first birds may begin to stir, their songs heralding the return of day. The transition from night to day has been marked by living creatures for as long as life has existed on Earth. Circadian rhythms, those internal clocks that synchronize biological processes to the 24-hour cycle, evolved hundreds of millions of years ago. Even single-celled organisms respond to the alternation of light and darkness, their metabolisms shifting with the turning of the planet. For humans, the dawn has always held symbolic significance. It represents renewal, possibility, the chance to begin again. The association of light with hope and darkness with despair runs deep in human psychology, perhaps rooted in the dangers that night once held for our ancestors on the African savanna. The New Year's first morning arrives gradually, not with the drama of midnight, but with the slow accumulation of light. The world transitions from darkness to luminosity through infinite gradations, each moment slightly brighter than the one before. This gentle progression mirrors the passage of time itself, which advances continuously rather than in discrete jumps. The day that begins now is the first day of a new year, a new chapter in the ongoing story of time. What it will contain is unknown. The future remains unwritten, full of possibilities not yet determined. The choices made, the events that occur, will shape what this day and this year become. Time offers both constraint and freedom. The physicist Max Planck, who initiated the quantum revolution in 1900, reflected on his own relationship to time and science. He wrote, "Science cannot solve the ultimate mystery of nature, and that is because, in the last analysis, we ourselves are a part of the mystery that we are trying to solve." This recognition applies doubly to time, which is both the object of inquiry and the medium in which inquiry occurs. The sun rises as it has risen countless mornings before, casting long shadows that shorten as it climbs. Light spreads across the landscape, illuminating hills and valleys, buildings and trees. The warmth begins to penetrate the cold of night, and the world awakens to another day. Somewhere a clock continues its patient measurement, its hands circling the dial, its mechanism clicking through the seconds. This clock does not know that a new year has begun. It does not distinguish midnight from noon, January from July. It simply counts, accumulating moments into minutes, minutes into hours, hours into days. The human significance of the new year is layered upon this mechanical rhythm, a meaning added by consciousness to the raw material of duration. Without minds to mark it, the year would turn unnoticed, one more orbit among billions. With minds to mark it, the year becomes an occasion for reflection, resolution, and renewal. In the light of morning, the themes of the night take on new coloring. The vast cosmic perspectives, the intricate scientific details, the philosophical puzzles all recede slightly as the practical day begins. Yet they do not disappear. The understanding gained in contemplation remains, informing the experience of time even when not explicitly attended to. The poet and mystic William Blake wrote, "To see a world in a grain of sand and a heaven in a wild flower, hold infinity in the palm of your hand, and eternity in an hour. This vision of infinite depth within finite things applies to time as well. Each moment, properly attended to, opens onto the whole mystery of temporal existence. The new year stretches ahead, its days and months not yet filled with events. It will bring what it brings, shaped by forces beyond any individual's control and by choices within the scope of human freedom. The balance between fate and freedom, between what is given and what is made, is played out within time's flow. As this reflection draws toward its close, the emphasis returns to the simple, irreducible fact of time's passage. The moments continue to arrive, to present themselves, and to pass into memory. This process cannot be stopped or reversed. It can only be experienced, witnessed, and perhaps accepted. The physicist Brian Greene has written extensively about time for general audiences. He notes, "Time holds us captive, it bounds our experience and limits our explorations. It's a cage from which we've sought release since we first recognized its power." Yet he also finds in this captivity a kind of gift, for it is time that makes experience possible, that allows stories to unfold. The captivity is also an invitation. To be bound by time is to be given the opportunity to live, to experience, to participate in the unfolding of reality. Without time, nothing could happen. With time, everything that has ever happened becomes possible. The morning brightens, the day begins, and time continues its endless progression. The clocks tick onward, each second adding to the accumulation of the new year. The Earth rotates, the planets orbit, the galaxies drift, the universe expands. At every scale, from the quantum to the cosmic, time's passage weaves the fabric of existence. The contemplation of time in the quiet hours of the new year has traversed many territories, from the midnight chime to the morning light, from the physics of relativity to the psychology of perception, from the age of atoms to the age of the universe. The exploration has ranged widely. Yet at its heart, the subject has remained singular, the mysterious, omnipresent, inescapable flow of time. In the end, time remains what it has always been, the medium in which all experience unfolds, the framework within which all questions are asked, the river on which all boats are carried. It is the most familiar aspect of existence and the most profound mystery. It is the enemy against which we struggle and the gift without which we could not be. The ancient Roman poet Horace coined the phrase carpe diem, seize the day. This exhortation to make the most of present time has echoed through the centuries, a reminder that time's passage demands response. Each moment offers choices. Each day presents opportunities. The recognition of time's limits can be a spur to engagement rather than a cause for despair. The calendar has turned. A new year has begun. The clocks continue their patient counting, marking the passage of moments that accumulate into minutes, hours, days, months, and eventually another year. Time flows on as it always has, as it always will, carrying all things with it toward whatever awaits. The light of morning fills the sky. The stars have faded into the blue. The sun climbs higher, warming the air, illuminating the world. Somewhere a clock ticks steadily, measuring what cannot be measured, marking what cannot be marked, counting the uncountable moments of existence. And the earth turns on, carrying its passengers through another day, another year, another moment in the infinite expanse of time. The galaxy wheels through the void. The universe expands in silence, and time, that strange dimension within which all things unfold, continues its eternal passage, unmoved and unmovable, the stage upon which the cosmic drama plays out. In quiet rooms around the world, clocks continue their steady rhythm. The hands circle, the digits change, the seconds accumulate. The measurement of time proceeds without pause, without judgment, without awareness of its own profundity. And within this measured time, consciousness stirs, reflects, wonders, and returns to the simple fact of being present in a moment that is always now.